Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to figure out how to calculate the pH of salts. And in this problem, we're adding 5 grams of potassium fluoride into a 1 liter solution. And as you can see, this substance is a salt, okay? It doesn't begin with hydrogen, so it's not an acid. It doesn't end in hydroxide, so we know it's not a base. So we call this a salt. Okay, this is an ionic compound or a salt, and our job is to calculate the pH of this salt called potassium fluoride. Okay, so the very first thing that we're going to do is we're actually going to figure out the molarity or the concentration of this solution. So we're going to change these grams into moles. So we're going to convert the grams into the moles. I'm going to add 1 potassium and 1 fluoride from the periodic table to get the molar mass, and that comes out to 58.1 grams per mole. So when we take the 5 grams and divide it by its molar mass, we're going to figure out that this thing has the amount of moles is going to be 0.0861 moles of Kf. Now, to get the molarity, you got to take the moles and divide it by the volume in liters, and we have 1 liter here. So it's going to be really simple. We're going to divide this by 1 liter, and therefore we get the molarity to be the same exact number of 0.0861 molar Kf. Okay. Now that we got the molarity, okay, we need to kind of like analyze this kind of this substance. Okay, so we're going to do what we call a BCA. We're going to take the Kf and we're going to ionize it, or it goes through the dissociation process, okay? And I like to use something called a BCA whenever there's a single arrow. And I'm going to take this molarity of 0.0861 and I'm going to place it in there for the Kf. Of course, what happens when there's a single arrow, everything pushes to the product side. So this is going to go down by 0.0861, and there's going to be nothing left, okay? And if this goes down by 0.0861 on the left-hand side, well, then on the right-hand side, it's going to increase by that same number because of a 1-to-1-to-1 ratio between the reactants and the products. So in the end, which is after, okay, we have 0.0861 molarity of K ions and 0.0861 molarity of F ions, okay? And we need to analyze each of these ions as being conjugates, okay? So the K ion, okay, is the conjugate acid of the strong base potassium hydroxide. So if this is potassium hydroxide, when it ionizes, it looks like this. And this is where we have to analyze things as far as conjugate acids and bases are concerned. And this was done in a previous video, so if you're a little bit lost at this point, you might want to go watch that video on conjugate acid-base pairs. But basically what it says, if KOH, which is one of our strong bases, if it's a strong base, then its conjugate acid, the potassium ion, okay, is what we'd call negligible. So it has no effect on pH. So I am not worried about the potassium ions, okay? What about the fluoride ions? Well, the backstory on the fluoride ions is it is derived from hydrofluoric acid, okay? So here's the potassium ion and here's the fluoride ion, okay? And the backstory here is that this is going to ionize partially, okay? So if hydrofluoric acid's a weak acid, then the fluoride ion is going to be what we call a weak base. And weak bases do have an effect on pH. So we are very concerned about the molarity of the fluoride ion because it is a weak base. And weak bases have an influence on pH, okay? Where this ion, the potassium ion, is a negligible acid because it's the conjugate of something that's strong. So basically, if you're strong, your conjugate is negligible, okay? But if your acid is weak, then the conjugate base is going to be weak as well with that inverse relationship, okay? So that's a little bit of review from what you got from the previous video. So the thing that influences the pH is going to be this conjugate base called the fluoride ion, okay? This next part is the part that most students mess up on, and that is, well, what do I do with these fluoride ions? Okay, the idea here is that you're going to write a good equation of the fluoride ion acting like a base. And what do bases do? They accept protons, okay? And it's going to accept a proton from a water molecule, okay? So this water molecule is going to actually act like an acid and donate its proton to the fluoride ion that's acting like a base, and it's going to accept that proton. When it accepts the proton, it makes hydrofluoric acid, and then what's remaining over here after proton donation is going to be the hydroxide ion, okay? So we're going to make an ice chart with this because this is an equilibrium arrow, and we're going to take this 0.0861 number, and we're going to plug it in right here, 0.0861. Remember, when you're doing an ice chart, water has no effect on equilibrium, okay? We are not told that we began with any hydrofluoric acid or hydroxide ions. All we know is there's 5 grams of potassium fluoride put in here, so we don't have any of this stuff, okay? We know this is going to go down X, this is going to go up X, this is going to go up X. This is 0.0861 minus X, this is X, and this is X. And that part, if you don't understand the stuff that I just did up there, you'll want to rewatch the video on weak acids and bases as far as calculating their pH, because that's how we're wrapping up this problem, okay? Now, to wrap up this problem, okay, we need the Kb value, because if this is a base, we need the Kb value, but we don't have it, okay? So the new part of this video series is understanding the following equation that I'm going to put in right here in the center, okay? And that is Ka times Kb is equal to Kw, and this is only true if it's an acid-base conjugate pair, okay? So when we go into our appendix, okay, in our textbook, there's no such thing as the fluoride ion, and I have it right here for you, okay? So if we look under the bases, you'll never find any fluoride ions in here. But if you come to the acid side, you'll see it's acid-base conjugate pair of hydrofluoric acid. So we're going to end up having this Ka value that we can look up, okay? And if we have the Ka value, and of course we know that Kw is equal to 1 times 10 to the negative 14, well then we can calculate the Kb value that's necessary here, okay? So I'm going to go into the appendix, and I'm going to look up the value for hydrofluoric acid, and I'm going to input it right here, okay? And when I go into the book, it says that Ka is equal to 6.8 times 10 to the negative 4, yep. And that's going to be equal to Kb, right here, okay? Ka times Kb is equal to Kw, okay? So if I want to figure out this Kb, I'm going to divide by the Ka on both sides, and I figure out that Kb is equal to 1.47 times 10 to the negative 11. I feel really good about putting that number in here and using the approximation method, because if we have times 10 to the negative 11, this shift is going to be really, really small. So I feel like we can approximate this to 0.0861 because of how small this Kb value is, okay? And then kind of like the rest is history. This is all stuff that we already know how to do. So Kb is going to be equal to the products, x times x, which is really just x squared, divided by the approximated value of the concentration of fluoride ions, okay? And that's all equal to 1.47 times 10 to the negative 11, okay? So if I cross multiply, okay, and then I would get x squared is equal to 1.27 times 10 to the negative 12. Of course, take the square root on both sides, and that's going to give me 1.13 times 10 to the negative 6, okay? Well, this value of 1.13 times 10 to the negative 6 is the concentration of the hydroxide ions, and that part's really important to me because if I take the negative log of that, I will calculate the POH, because the POH is a negative log of the concentration of hydroxide ions. So I'm going to plug that number in there to get the POH, okay? And the POH ends up being 5.95. If I do 14 minus that answer, I will get the pH. So 14 minus 5.95 gives me a pH of 8.05, and that's the answer to the pH of the solution. So for quick review, the first thing that we did is we figured out the molarity of the KF, okay? It goes through the process of dissociation, or it goes through the ionization process where it splits up into its ions, and we analyze this. We analyze both of them. This ends up being a negligible acid, okay? But the fluoride ion ends up being a weak base. So we write a base equation for it, okay? But to get the K for the base, we have to use the K of the acid, okay, with Kw to calculate the Kb. And as soon as we have the Kb and the initial concentration, we can do our equilibrium work with using the ice chart to calculate POH and then eventually to pH, okay? If that last part, like I said, is too much over here, you need to go back and review kind of like the calculating the pH of weak acids and weak bases. But if you found all this information helpful, please give it a like or subscribe. I'm going to do 2 more videos of pHs of salts, and hopefully that will help you kind of like master this technique, because it is a difficult problem, okay? So just keep working at it and you'll get there. So once again, like and subscribe. When you have that comment, it pushes out the information to other students that are interested in learning chemistry.